Modelling with differential equations, example 1. The rate of increase in a population of bacteria is given by the differential equation dn dt is equal to 0.33 n. Initially, there are 2,000 bacteria present in the colony. N is the number of bacteria and t the time in hours. Find a model for n in the form n equals ae to the kt. Find to the nearest 10 the size of the population after 3 hours. What is the average rate of change in the size of the colony over the first 3 hours? Find the time at which the population is 100 times its initial value, and why is this model not realistic in the long term? So let's go back to A, where we find a model, and that means solving the differential equation. So this is a separable differential equation, and so we can separate and integrate. So we've separated now, and that gives us natural log of n is 0.33t plus a constant. Taking the exponential function of both sides and remembering that the exponential function and the natural log are inverse functions, when we do e to the log n, we just get n. On this side, we get e to the 0.33t plus a constant, but we can use our index laws here to split that into e to the c, e to the 0.33t. Remember, in this situation, we would add the indices. Now, this is a step that I might shortcut in future examples, but e to the c itself is a constant, and so we could just call it a. We know that n is 2000 when t is 0, and that means that a is 2000 because, of course, e to the 0 is just 1. So we have that n is 2000 e to the 0.33t. In part B, we want to find to the nearest 10 the size of the population after 3 hours. That's just a case of substituting in t equals 3, since t is the time in hours. So we put in t equals 3, and we calculate. So that's approximately 5,380. In part C, we want the average rate of change. When t is 0, we know n is 2000. When t is 3, n was 5,382.47, and so on. The average rate of change would be the gradient of this straight line segment. In other words, it's the difference in the y's over the difference in the x's. So that would give us 1,127.5 bacteria per hour. So now in part D, we want to know when it's 100 times. So instead of being 2,000, it would have grown to 200,000. Well, that gives us, just dividing both sides by 2,000, that e to the 0.33t is 100. Taking the natural log of both sides, and remembering once again that the natural log and the exponential are inverse functions, we get 0.33t is the natural log of 100. So t is log 100 divided by 0.33, and that's 13.96 hours. So why is this model not realistic? Exponential growth cannot continue in this way. If it did, the entire planet would soon be made of these bacteria.